next topic is a little different. So we're going from oscillations to talking about fluids. Fluid is anything that needs a container to keep it in place. So liquids are fluids, gases are fluids. So both liquids and gases fall under this category. When we talk about fluids, we don't tend to talk about the mass of our fluid or the forces we apply. We tend to talk more about density and pressure. The symbol we use for density is a Greek letter, rho. R-H-O. So rho for density is the ratio of mass per volume. So the amount of kilograms you can shove into a certain volumetric area, volumetric space. The more mass you have in a smaller volume, the greater the density is. So the SI units that we're going to use for density will be kilograms per meters cubed. You do have a chart in your book that shows densities of some different materials. It's by no way extensive, but it does have some of the materials that you'll need. Water, for example, the density of water is 1,000 kilograms per cubic meter. Now, when we talk about forces, for example, I have a container of ice water here. I can't push with my finger and expect anything to happen. My finger just gets wet. So a force in and of itself, not too useful. We need to apply a force over an area in order to be able to get something to happen here. Pressure is that ratio. So pressure is capital P. It's the ratio of force per area, cross-sectional area. So for example, if we wanted to increase the pressure for this water, we would need a piston of some sort that would fit perfectly in this circle that we could then push on the piston. So the whole entire surface area would be covered and it wouldn't let water leak out. It wouldn't let the piston go all the way in and just get wet rather than exert a force on it. Okay? It's convenient that it turned on for me since I wanted it on. I forgot. Okay, so pressures, density, those are a couple of, I don't know what word I'm looking for. A couple of things we need to know.
Measurements. Important.
That works, measurements. Now pressure. The SI units of pressure are newtons over meters squared. Force over area. We call this a Pascal, and we use a capital P with a lowercase a to represent it. So if you see a value listed in pascals, that means the same thing as newtons over meters squared. We can easily convert from other pressure systems, for example, atmospheres, ATMs, is something we're probably fairly familiar with. Atmospheric pressure at sea level is 1 ATM.
Is that a bar too? 1 bar is 1 atmosphere?
I can't remember. Is it the same?
Yeah, use that in diet.
And is it a torr too? I can't remember. There's so many pressure systems out there. Pounds per square inch is another one.
So PA is Pascal.
Pascal, yeah.
Pascal. How do you spell it?
P-A-S-C-A-L. Millimeters of mercury is another one. Pressure. So there's a lot of different measurement systems. The most common ones we're going to see will be atmospheres, and then pascals is what we'll need our units to be in when we solve our problems. The conversion. 1 ATM is 101.3 kilopascals, or 101,300 pascals. Conversion's in your book. You don't have to memorize it, but you need to be able to do the conversion. So if you have a certain number of atmospheres, ATMs, then you need to be able to figure out how many pascals that is.
Oh, it's a small unit.
Yes. Okay, one other piece of terminology that you'll see in our problems is called gauge pressure. For example, if you take your little gauge to measure the pressure in your tire on your car, you're measuring a gauge pressure. Gauge pressure is the difference between the pressure outside minus the pressure inside, or vice versa. So when you put your little gauge on your tires, my tires are supposed to be 33 psi. That doesn't mean the absolute pressure inside my tire is 33 psi. That means the pressure inside of my tire is 33 psi higher than outside. Okay, outside's well, pretty close to 1 atmosphere. Inside is 33 psi higher than that.
And that's the cold tire.
Yes. Yeah. Temperature will certainly change that. So gauge pressure is the difference between outside and inside.
Of the vessel.
Yes. So, for example, another example, all the fire extinguishers they have in the hallways. The fire marshal has to come once a year and check the gauge on each of those. There has to be a certain gauge pressure. The pressure inside the canister needs to be bigger than the pressure outside the canister. If the pressure was the same, there would be no net force trying to push the fluids out of the container. So it would be absolutely useless. Yeah, it's like everything in that would be kind of cool.
Somewhat related to, so it's the delta though of the atmosphere you're at.
Correct.
So, you know, if you took your fire extinguisher to sea level from
It would may work a little bit. Yeah. So pressures, when we talk about forces with fluids, we tend to talk about pressure. If there is a pressure difference, then you can get a net motion of an object. Favorite example. Any of you have shower curtains in your shower? How's that for narrowing that down? Have you ever noticed when you turn the water on, you get attacked by the shower curtain? That's because it is annoying. I totally agree. It turns out if you make fluids flow, if you make them move, that automatically decreases the pressure in the region where the fluids are moving. Good example, if you take a piece of paper, put it right under your lip, and blow, the motion of the air above causes the pressure to decrease. Below, the pressure is still whatever the atmospheric pressure happens to be here. That pressure underneath is bigger than the pressure above, causing it to rise. Okay? The airplane wing, exactly right. Lift. So that's what's happening in your shower. The motion of the water inside the shower is decreasing the pressure, whereas the rest of the bathroom is still at your normal atmospheric pressure. Pressure's bigger outside the shower than inside the shower, so it pushes on the shower curtain and attacks you. And it's annoying. Okay. Another example. These are just suction cups. I'm sure we've all seen a suction cup at some point in our life. I believe these are the ones they use like to move those big pieces of glass. When you take a suction cup and push it against the wall, the window, whatever, you're pushing air out of that region. Okay? Air pressure, the whole concept of air pressure is from the amount of particles, air molecules that are hitting you. We're being collided with air molecules all the time. If you get rid of some of the air, that's going to decrease the pressure because you're going to have fewer molecules that can hit. So when I take my suction cups, in this case I'm just going to push them together, when I push them together, that pushes some of the air out from between them. So that decreases the pressure. The pressure in between these suction cups is now smaller than the atmospheric pressure around it, which makes it really hard to open them. Pressure outside is less than the pressure inside. Okay? So pressure differences basically can give you a net force. Yes?
Can you calculate the tension that you have to pull on that based on how much?
In this case, we would need an actual force probe to
Because
measure
of
it.
elasticity.
If we don't have enough information to calculate it. You would need to know the volume that you ended up with inside of there. And that's not something that would be easy to calculate in this case.
So, but if you ended up saying if you had absolutely zero volume, you wouldn't have.
You'd
if
have
you took it
absolutely
all
no
out,
pressure.
You would have no pressure. You'd have no
Right.
suction. So
Well,
there has to
No,
be.
there's still be, the suction is due to the pressure difference.
Right.
If there was no volume in there, if you were able to push out all of the air,
have
you would essentially have a vacuum.
Right, because
Which would be
you
low
have
pressure.
volume with nothing in it.
Yes.
And so you have.
So you'd have really low pressure.
So you could
Still normal
calculate
pressure outside.
the perfect scenario, which we could never reach.
Right.
Okay.